Hello, my geometry peeps. Today we're going to be talking about geometric probability. And in this unit, we are talking about area and perimeter. So we're going to continue those concepts, but now we're going to talk about chances of things with area and perimeter. And chance or likelihood or probability, that's all the same stuff. So what you're going to need is your notes, foldable, calculator, pen or pencil, all that good stuff. Okay, so the general probability of something is the chances that something will happen. So in order to figure that out, there's like a formula, if you will, which is pretty self-explanatory. The chance of something happening for a probability is the outcome that you want or the favorable outcome over the total possible. So this is like the definition and this is like the formula. And when we're talking about geometric, we'll be talking about a region over an entire region. So if we're talking about the probability of drawing a king out of a deck of cards, the favorable outcome is we want a king. So there's 4 kings in a deck of cards out of how many total possible cards are there? 52. So if you simplify that fraction, it's 1 out of 13. The probability of a fire drill happening during our class time, well, that's going to be like, say we have an 80-minute class and we know that the fire drill is happening, I don't know, next week, Tuesday or something. It'd be 4 mods out of the 22 mods of a given day. If we're trying to figure out the probability of rolling a number on a dice, we'll assume it's a standard dice divisible by 3, then on a, oops, I spelled dice wrong. That's funny. Classic math teacher spelling things wrong. You know me. Okay, but dice have the options of rolling a 1, a 2, a 3, a 4, a 5, or a 6, if we're talking for standard dice. So out of those numbers, only 3 and 6 are divisible by 3. So our probability then would be 2 out of 6, or 1/3. When you talk about the chances of something happening or the likelihood, you can write it as 1 out of 13, or you can do 1 to 13, or you could even give me the percentage, like in this example, 33.333%. So like I said, geometric probability then involves geometrical shapes and finding the chance of landing in a certain region, and that's going to be using our area stuff that we've been learning. So we're going to have a region that we want to fall in over the total region that we could fall in when we think back to that probability formula. So examples are like carnival games, so like pin the tail on the donkey, getting a dart on a certain portion of the dartboard, bouncing a ball into a bucket, or tossing a coin, or bouncing the ping pong balls into the fish bowls at the carnivals so you can win a goldfish. That's the kind of probability that we're talking when we talk about geometric probability. Okay, so for our first example, we need a little bit of background. So a ship recovery mission. A ship is known to have sunk off the coast between an island and the mainland. A salvage vessel anchors at a random spot in this rectangular region, and divers and sonar attempt to locate the ship. So you guys, this isn't just a problem that Mrs. Littlefield decided to make up. This is a real thing. Like when people hunt for treasure, they grid out longitude and latitude to come up with a rectangular region or somewhat of a rectangular region, or the outline a region in the sea, in the middle of the ocean. They'll be like, okay, we need someone to cover this, but our boat can only reach so far. So if this was our picture, that's our rectangular region, and our boat has a radius of 500 feet. So 2 things to note for this example is that 1, our picture is not drawn to scale. First of all, the boat's measurements are labeled in feet, and the rectangular region is measured in yards. So this is definitely not even close to what the boat could cover, right? Like the rectangle should be way bigger if we want to draw it in proportion to what's actually going on. So when why the boat can't move, if that's what you're thinking with this problem, why can't they just move and keep moving? When people, divers, sonar, all that stuff, it's not like they're just freely swimming with their scuba gear into the ocean for miles upon miles upon miles. They have to be anchored or tethered to the boat. So in order for that to happen, that's why there's a radius of 500 feet. Those sonar divers can't go out any farther because of the ropes that are connected back to the boat. So the boat has to anchor and they can only work in circular pieces. So they could keep moving, but it's going to take a while. They have to figure out the first circle, and then once they're done with that circle, they'll have to move to another section that they haven't even covered with a different spot for their radius to reach everywhere. So we're trying to figure out if a diver can only search within this 500 feet in this region, what is the probability that they'll find it on the first attempt in that first part where they anchor? That's what we're trying to figure out. Do they have a really high chance or a really low chance, or is it 50-50? That's what we're trying to figure out. So, like I said, this picture is not drawn to scale, and the units are not the same. We have yards and we have feet. Well, it's going to be easier for me to convert yards to feet rather than this 500 feet to yards. So first off, we need to convert 2,000 yards. We have to multiply it by 3 to get 6,000 feet, and 5,000 yards need to be converted to 15,000 feet. So how we're going to find the probability is the area of the circle over the area of the rectangle. And now that we have everything in the same units, that's okay. So my probability then, the area of the circle is going to be 500, which is my radius, squared times pi, all over the area of the rectangle is 6,000 times 15,000. And 500 squared is 250,000. So 250,000 pi all over. If we take 6,000 times 15,000, we get 90 million. 1, 2, 3, 1, 2, 3. And if we convert 250,000 times pi, that decimal is a really big decimal that we're going to divide by 90 million. 1, 2, 3, 1, 2, 3. Sorry, I'm punching this into my calculator right now. But if you convert all of this to a decimal, convert to decimal, we get a decimal of 0.00872664663. That's what my calculator tells me. Well, if we want to find the probability, we can find that percentage or multiply by 100, and we get, when we multiply by 100, 0.87%. You guys, that's not 87%. This decimal is telling me almost 1%. It's roughly almost 1% for that ship to find it on the first dive with sonar than it is for them to keep going. So that's my answer, is about 1%, or if you want to go a little more accurate, 0.87%. That's how likely that boat would be to find that vessel. All right, so let's try some more example problems, specifically with carnival games. So we are tossing a beanbag in an open space on the board in order to win a prize. So the first question is, what is the probability of our beanbag landing in the nose? So remember, probability is like what we want to happen out of the total possibilities of happening. So for our purposes, we want the probability of it landing in this triangle out of the probability of it landing on the entire board. So we need to find the area. So the probability is going to be the area of the triangle over the area of the rectangle or the whole board. I'll put board in parentheses. So the area of that triangle is then just going to be 18 times 15 times 1/2, which is 135. And if we find the area of the whole board, that's just going to be 90 times 140, which is 12,600. And if we divide that in our calculator, we get a decimal of about 0.010714, blah, 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 blah. So if we move the decimal over 2 spots or multiply by 100, our probability is approximately 1.07%. So we have a really small chance of getting that beanbag in the triangular portion of the board or in the nose of the image, if you will. Now we have to find the probability of the beanbag landing in the eyes. So we're going to have to find the area of those two rectangles out of the total. So our probability is going to be 20 times 15, but there's two of them, so times 2. A lot of the whole board is still 12,600. And so 20 times 15 times 2 would then be 600 out of 12,600. And if we find that decimal in our calculator, we get about 0.047619, or probability is roughly 4.76%. So that's our probability of landing the beanbag in the eyes. And now they're asking me to find the probability of winning a prize. Well, in order to win a prize, my directions tell me we have to throw the beanbag into any open space. So the probability now is going to be of the eyes, of the nose, and of the mouth, or the 5 circles. So we need the probability of all that green stuff out of the total. So my probability is going to be, we already found the total for the nose, which is 135, plus the total for the eyes, which is 600. Now we have to find the probability of falling in the mouth. Well, one circle, the area of a circle is going to be pi r squared. So our radius is 6, so it's going to be 36 pi, but there's 5 of them, so we have to multiply that by 5. So 36 times 5 is 180. So we have 135 plus 600 plus 180 pi all over the 12,600. So if we convert that numerator to a decimal, we get like 4,86678 all over 12,600. I wouldn't actually round necessarily. I just punch in what 135 plus 600 plus 180 pi is, and then in my calculator keep the answer button and then divide by 12,600. And so when we get that decimal, our probability is about 10.32%. Sorry, I'm running out of room, but it's about 10.32% in order to win a prize. Okay, so a point is chosen at random along the segment. We need to find the probability that the point lands between, I know it says that the point is on, but we're trying to see if it lands somewhere on this entire segment. So somewhere in between A and B. Well, from A to B, it's 2 units long, 1, 2, and from A all the way to the end it has 18 units. So the probability of a point landing between A and B is 2 out of 18, or 1/9, or about 11%. Now if we want to do, I'm going to do a different color, I'll do yellow. If we want to find the probability that it lands between B and D, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have a distance of 9 out of a total of 18. So it could land in 9 units worth along that number line out of a total of 18 on this number line, which would be 1/2 or 50%. So I know it says the point is on, but we're going to also know that that means between the values that we've been given for those two problems. Okay, so if we pick a random spot on the trapezoid, or if we had a trapezoid on the ground or something and we were dropping a coin on it, we're asking what's the probability that it lands in the blue regions, or that the spot that we randomly pick with our eyes closed is on the blue regions. So we need to find the probability, which would be the blue regions, regions out of the entire trapezoid. That's how we're going to find this probability. So we first have to figure out the area of the blue region. So for this triangle on the right, 4 times 4 is 16, times 2 is 8, so my area for that triangle is 8. Well, I know that opposite sides of rectangles are congruent, so that distance is 7, that distance is 4. We know since the whole bottom base of the trapezoid is 16, Then we know if 16 minus 7 minus 4 is 5, this tiny section is 5. So from here to here is 5, and from there to there is 7, and then from there to the end is 4. So now if we take 5 times 4, base times height times 1/2, we get an area of 10. So the blue regions added together would be 10 plus 8, or 18, and now we have to do it out of the total. Well, the only area that we haven't found yet in the trapezoid is the rectangle, so we should just take 7 times 4, which is 28. Then if we add 10 plus 28 plus 8, we get a 46 for the whole entire area of the trapezoid. You could also use the trapezoid formula that we know, which is 1/2 times the base plus the base times the height. Either way, however you want to do it, you're going to get 46 units squared for the area of the entire trapezoid. And then when we take 18 divided by 46, that decimal for our probability was 0.3913, blah, 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 blah. So our chances are 39.13%. And that is all that I have for you guys. So thank you for taking such good notes, and I shall see you soon. And when you get to class, if you have any questions about probability in general, geometric probability, area formulas, please don't hesitate to ask me. I'm always here to help. So get these notes written down, and I'll see you soon.